Hi everyone, welcome to week 6 of Incomplete Data Analysis, and in this week we will continue studying maximum likelihood estimation when there are missing values. We have seen in the last week that under ignorability we can obtain maximum likelihood estimates for the parameter of our complete data, the parameter that we would be interested in case there were no missing values, by simply maximizing the likelihood of the observed data. And we have seen that ignorability requires the missing data to be missing at random or missing completely at random, and that the parameters of the missing data model and of our data model, they need to be distinct. And informally stated, distinct means that the missing data model does not contain information about the parameters of our complete data model. Okay, let us start. And I've started saying that under ignorability we can simply maximize the likelihood of the observed data, but the likelihood of the observed data can be a tricky quantity to work with, or at least to maximize analytically. And in this first part, we have an example that illustrates precisely this. So our context is the following. We have two variables, y1 and y2, and we assume that y1 is fully observed and that y2 has some missing values. And to think of a concrete example, so things are not so dry, let us suppose that we are under a context of a medical study, and Y1 represent measurements of some outcome of interest at baseline. Baseline is at the beginning of the study, and then Y2 represents the outcomes measured at some follow-up time. And basically, under this context, it means that all individuals have their outcome recorded at baseline, but some do not have their outcome measurement at the follow-up time. And we will be assuming that that y1 and y2 follow the vector composed by y1 and y2 follows a bivariate normal distribution, and we have that the mean vector is formed by mu1 and mu2, and we have the variance covariance matrix. And because we will need it later, we have here what is the density for the bivariate normal distribution, and this quantity here is the determinant of the variance covariance matrix. And under the bivariate, this is the density function for the general multivariate normal distribution. In this case, we have the particular case of a bivariate normal distribution. Nonetheless, we can still write it in this way, but we will not look at it. But in fact, assuming that we have a bivariate normal distribution, the determinant and the quadratic form here, they have an expression that we can replace. But for us, it suffices to work with this, just to make the point that because it's a bivariate normal distribution, in fact, we know what the determinant of the variance covariance matrix is, and also we can have an expression for the quadratic form. But let us now go to our setting of interest. And okay, our setting of interest is to make inferences or maximum likelihood estimation for, not inferences, in this case it's only estimation. So we are interested in maximum likelihood estimation for the parameters of the bivariate normal distribution. And these are the mean vector and the covariance matrix. And for an individual y, say, we have that the full data is given by y1, y2, and R. R is the missing data indicator, and without loss of generality, just because it simplifies the maths or what we write down, let us assume that the y1 is fully observed, but that y2 has some missing values, but we can always rearrange in such a way that the first m values of y2 are observed and the remaining n minus m values of y2 are missing. And if this is the case, we know that R, our missing data indicator, will take the value 1 for I from 1 up to m, and will take the value 0 for I from m plus 1 up to n. And we know that the full data, we for the individuals with missing values, we do not observe their full data. What we observe is their y1 measurement and the missing value indicator that will be 0. But we do not observe this triple here. But we have already made this point last week. We know that our full data model of interest is the one that we have here, right? Is the model for y1, y2, and r, given the mean vector and the variance covariance matrix. These are the parameters from our data model from the bivariate normal distribution. And then I have psi that are the parameters for the missing data model. But now I will, to proceed, I will assume ignorability. So I assume that y2, the missing in y2 is missing at random or missing completely at random, and that the mean vector and the variance covariance matrix are distinct from psi, right? So the parameters from our data model are distinct from the parameter or parameters from the missing data mechanism. And as I have said, uh, uh, distinctness, sorry, of the parameters implies that the parameter space is equal to the parameter space of the joint parameters of mu and sigma and of psi is equal to the Cartesian product of their individual product spaces. But basically and informally stated, as I've mentioned at the beginning of the video, this means that the model for the missing data mechanism does not contain information about the parameters of the complete data model. And so, as we have seen in the last lecture, when we have the product of the missing data mechanism and of the observed of the likelihood, sorry, of the observed data, then if the parameters are distinct, if the missing data, if the model for the missing data mechanism does not contain any information about the likelihood of the observed data, when I'm maximizing with respect, say, to the parameters of the likelihood of the observed data, the model for the missing data mechanism acts as a constant, right? So I do not need to care about it. I can just maximize the likelihood of the observed data. And again, I've made the point on last week, but again, ignorability does not mean that we are ignoring the missing data mechanism. We have arrived at the conclusion that we can use the likelihood of the observed data because we have assumed that the missing data are missing at random or missing completely at random, and that the parameters are distinct. And so we are not ignoring, we are placing constraints or conditions, or we have made assumptions about our missing data mechanism. And basically, ignorability means that I don't need to posit a model for the missing data mechanism, and that really simplifies my life. But okay, this would be the if I was not willing to assume, or not willing, no, but this is the joint density for our full data model. But because I'm assuming ignorability, I know that I will work with the likelihood of the observed data. And okay, so let's construct the likelihood of the observed data. Remember that I have y1 and I have n individuals and they are all observed, and then I have y2 that has some missing values, and we have said that the first m are observed and n minus m are missing. And so the likelihood of my observed data needs to take in consideration this part and this part, right? What I observed y1 entirely and the first m observations of y2. But remember that y1 and y2, they have some joint structure because they follow a bivariate normal distribution. And so what I have here, or the likelihood for the observed data, it's constructed in this way. Here I have, for the first m observations, I know that the contribution to the likelihood, sorry, it's not the log likelihood, to the likelihood is the joint density of y1 and y2. Basically, I'm looking at this part here. Okay, this is what I have here in this first part of my likelihood. But then I still have this part here, the remaining n minus m observations in y1 that I observe, and so I need to include them in my observed data likelihood, but I do not have the corresponding y2 observations because they are missing. And so in this part here, that's exactly what I have. It's the contribution of the last n minus m observations from y1. So I hope it is clear. This first part here in red, it's the contribution of the first m pairs of y1 and y2, and then in green, it's the contribution of the last n minus m observations from y1. And I know that here I'm using, for this first part, what I have here then is that I have used what I have in a previous slide, is the density of the bivariate normal distribution, and the properties of the bivariate normal distribution say that the marginals, they follow a normal distribution with parameters. I know that my mean vector is mu1, mu2, and so I know that the mean of y1 is mu1, and I know that the diagonal of the variance covariance matrix is sigma 1 squared, sigma 2 squared, and then I know that the variance of y1 is sigma 1 squared, and so this is just the density of a univariate normal distribution with mean mu1 and variance sigma 1 squared, and that's what I have here in this green part. And so what is y observed here is y1 up to yn, and y1, sorry, from 1 up to n, all the observations from y1, and the first m observations from y2. And these likelihoods, okay, now this is the likelihood of my observed data. If I want to estimate my parameters, or to obtain estimates, maximum likelihood estimates of my parameters, of my mean vector and of my covariance matrix, I just need to maximize this likelihood. But because I have the product of a bivariate normal density by the product of univariate normal density, the score equations for the mean vector and for the variance covariance matrix, so my score equations, they are not trivial to solve. We could cross analytically we could cross our fingers and code this likelihood function or the corresponding log likelihood and send it to some software. But in this case, we can do better. And this is a typical example in the missing data literature, because this likelihood of the observed data is kind of tricky, and with more general patterns of missing data, it has the potential to be even trickier. But I can, in this case, come up with a factorization that actually will simplify my life, and I will be able to obtain analytically maximum likelihood estimates for my quantities of interest. So let's proceed. Uh, some known facts about the bivariate normal distribution that I will use. Remember that my likelihood is the product of the first m observations of the joint density of the bivariate normal distribution times the univariate normal distribution for n minus m observations coming from y1. And somehow what is making my life difficult is that contribution from the bivariate normal density. And I'm sorry. As we have already seen, the marginals are normally distributed, but a good fact is that the conditional distribution, in this case we are looking at the conditional distribution of y2 given y1, is also follows a univariate normal distribution with some parameters, with mean given by beta 0 plus beta 1 y1, where beta 0 and beta 1 are defined here, and then some variance that I have used sigma 2 given 1 squared, and that it's given by this. So basically I'm using the parameters of the mean vector and of the variance covariance matrix. But the good thing is that the conditional distribution of y2 given y1 follows a univariate normal distribution with these parameters. And the point now is, remember that for any joint density, right, I can use Bayes and say that and as we have seen, this is univariate, this is univariate. Okay, so let's proceed and see the example in more detail. So this is exactly what I have just written. I can write the joint as the product of the conditional distribution of y2 given y1 times the marginal distribution of y1. And I know the parameters. I know that the marginal depends on parameters mu1, sigma 1, and the joint depends on beta 0, beta 1, and sigma 2 given 1, and we have what they are in this previous slide. Of course, they are written as a function of the parameters of the mean vector and of the variance covariance matrix. And so we can think of our new parameter, the parameter that contains the elements of the marginal and of the conditional distribution. And I know that these are my parameters, and it's important for what will come next that the parameters of that are in phi, the parameter, the vector that collects the parameters of my conditional and my marginal distribution, they are in a one-to-one correspondence with the parameters of my original model, and the parameters of my original model are the elements of the mean vector and the elements of the variance covariance matrix, and they are here. It's mu1 sigma 1, mu2 sigma 2, and the covariance between y1 and y2. And we see that theta and psi, they share mu1 and sigma 1, but then we have beta 0, beta 1, and sigma 2 given 1, and then for in theta we have the mean, the variance, and the covariance. And saying that the parameter psi is a one-to-one function or is a one-to-one correspondence or mapping of the original parameter theta, it says that it basically means that I can write any element of psi as a function of the elements of theta, and this is exactly what I have here, right? I know that mu1 is mu1, sigma 1 is sigma 1, so they share these two parameters, but then I have written beta 0, beta 1, and sigma 2 given 1, the variance of the conditional distribution, and all of these parameters depend or are a function of the parameters that are in theta. And conversely, I can write the parameters that are in theta as a function of the parameters that are in psi, and these are written down here. So they are in a one-to-one correspondence. And the good thing, as we will see later, is that once we have obtained estimates for the parameters of one of the sets, we can go back to the parameters of the other set. Okay, and further, and this will also be very important, the parameters in psi and sorry, not the parameters in psi and theta, sorry, the parameters of this factorization, this one, mu1, sigma 1, and beta 0, beta 1, and sigma 2 given 1, they are distinct. And why? Because knowledge about, say, mu1 and sigma 1 does not imply knowledge about beta 0, beta 1, and sigma 2 given 1. And if we come here, we know that, okay, beta 1 is written as a function in particular of sigma 1, but just knowing sigma 1 is not enough to know the value of beta 1 because I don't know this. I don't have information about this in my set of parameters here, okay? Sorry, on mu1, sigma 1. That's it, okay? So they are distinct. And they are the parameters in psi. These are the parameters of the conditional and the marginal, and the parameters theta that are the parameters of the joint distribution. They are in a one-to-one correspondence. And further, when I do this factorization of the joint, that it's equal to the conditional times the marginal, the parameters of these two distributions, they are distinct. And so I go back to my original likelihood, correct? This is what I had before, and we knew that this was given, or we replaced the joint density by the bivariate normal, and this is the univariate normal. But now, because I can write this as f of y2 given y1 given f of y1, and I know that this is normal with mean beta 0 plus beta 1 y1 and variance sigma 2 even square, and this is normal mu1 sigma 1 squared. I further, this is then replacing the joint by the composition or the factorization of the conditional and the marginal, and this is what we had from here. This is this part, and this is this part. And now I see that I have the product from y from 1 up to m of the marginal, and also from m plus 1 up to n from the marginal. And so I can say that this is the product from y from 1 up to n of the marginal, and this is the product of the first m observations of the conditional distribution. And because I have said that, or I know from the properties of the bivariate normal distribution, that is a normal distribution with this parameter, so I can just come here and replace, and come here and replace. And the good thing about the parameters being distinct is now if I want to maximize this likelihood, I can maximize uh, I can maximize these two parts separately because the parameters are distinct. So if I maximize the second bit, I obtain the usual estimates for mu1 and sigma 1 squared. The mu1 is the mean and the sigma 1 square is the 1 over n, the sum of the squares, correct? And here, this is also a univariate normal distribution, and in fact, this is very similar to the calculations that we do for linear regression, right? We can have like estimates similar to what we have to the intercept and to the slope in regression analysis, like tedious calculations, but they are easy. So this likelihood from an analytical point of view is much more tractable from the one than the one, sorry, that we had in the beginning that had the product of the bivariate times the marginal. And basically what we have seen is, okay, because I know that the after I factorize my joint distribution as the product of the conditional times the marginal, and because the parameters in these two factorizations are distinct, and also the parameters, the new set of parameters is in a one-to-one corresponding, because they are distinct, I can maximize these two pieces separately, and so I need only to solve two simple problems. Okay, so I can obtain estimates for beta 0, beta 1, sigma 2 given 1, mu 1, and sigma 1. And then because they are in a one to one correspondence with my original set of parameters, then I already have mu1 and sigma 1, the estimates, but I can easily have estimates for mu2, for sigma 2, and for the covariance between y1 and y2. And after doing the calculations, that's where we arrive. As I've said, they are tedious. These ones are the typical ones from the normal distribution. It's the contribution from the second piece in the likelihood, and the other are the typical calculations for linear regression when we assume that the errors are normally distributed. So this is tedious calculations, but the point is that they are simple. Okay, and these are my estimates. Now, if I have assumed a complete case analysis, I would be disregarding the last n minus m observations from y1. And this is just to make the point, because in the last lecture we have seen an example of incomplete normal data, but because we only had one variable, we had done all the calculations. It was simple as well, because we just used the likelihood of the observed data. We assumed ignorability, but in that case the results coincided, as I have mentioned, with the results that we would have obtained from a complete case analysis. But here it's not the case, because remember that we had y1 and then y2 only had the first m observations. And so if I do a complete case analysis, basically I'm ignoring this part and I'm just retaining the first m observations of y1 and y2. Okay, and now that's it. And that's this example is the typical textbook example in missing in likelihood based inference for incomplete data, because it makes use of the trick of the factorization of the observed data likelihood. And it also emphasizes that because of the patterns of missing data, and here the pattern is simple, right? We only have two variables, and one of the variables is incomplete. It's not, let's say, a very difficult missing data pattern, but we already had to do something, because the likelihood of the observed data was not manageable, let's say, from an analytical point of view. But in this case, and this is not always the case, we were able to factorize the joint density, and further the parameters on the factorization, they were distinct, and that allowed us to maximize the different pieces of the likelihood separately. Okay, now let's do a small simulation study, and let's assume that the parameter that I'm interested in estimation is mu2, then I know that after rewriting the joint as the product of the conditional and the marginal, and after I do the tricks that I've mentioned before, I can obtain mu2, that is the parameters in the theta in my original set of parameters, but I can easily obtain mu2 by obtaining estimates of beta 0, beta 1, and mu 1, and these are defined here. Okay, so I can easily estimate mu2. And I will compare the results from with mu2 from a complete case analysis. So it just takes the first m observations of y2 into account. Okay? And what I have done is I have simulated 1000 datasets. Each dataset has 100 observations, and I have simulated data from a bivariate, standard bivariate normal distribution. So the mean vector is formed by zeros, the diagonal of the variance covariance matrix is formed by ones, and then we will see results for correlations that belong to the set, for correlations that are zero, for a correlation of zero between y1 and y2, for a correlation of zero point 0.5, and for a correlation of zero point 0.9. And we need to put these, we have derived these results under ignorability, so we need to put ourselves first, at least under the ignorability context, to see how things works. And so we have assumed missing at random data, and missing on y2 was imposed, so a value in y2 is missing if y1 is above some threshold, and the threshold is given by the quantile of a normal distribution, and we have said it's the quantile of a, and a is equal to 0.8, so this is clearly missing at random data, and also distinctness of parameters is satisfied, right? So okay, this is, and I will be comparing the estimate of mu2 obtained using a maximum likelihood estimation. That's what I obtained for mu2 using my observed data. So I used all observations that are available, the n observations from y1 and the m observations from y2, and I compare with the results from a complete case analysis for mu2 that just used the first m observations, the first bit. And when the correlation is zero, when the variables are in fact independent, maximum likelihood and complete case analysis, they give similar estimates, and this is no surprise because the estimator that we are using for mu2, this estimator here, in fact, when the variables are independent, it reduces to this quantity here, and we can easily see because it's beta 0 plus beta 1 mu1, and if you go back here and just replace, we know that beta 1, when the correlation is 0, the covariance is 0, so beta 1 is 0. So if beta 1 is 0, I know that my estimate for mu2 is only the estimate of beta 0, but the estimate of beta 0 also depends on beta 1, so this part is also 0. So I end up, sorry, that the estimate for beta 0 is the mean of y2, so formed by the first m observation. So when the variables are independent, complete case analysis and maximum likelihood estimate, they coincide in this case. And okay, we are not doing bad even in a complete case analysis. We know that they are independent, so basically y1 is not contributing with any information on the estimation of mu2, and that's what I get. Okay, now exactly the same thing, but the correlation is 0.5. We see that complete case analysis, the behavior starts deteriorating, right? Because we are ignoring the information that comes from y1 to estimate mu2, right? So whereas for maximum likelihood estimation, we are taking into consideration all information that we have available, right? So we are not discarding the n minus m observations that we have available in y1, and that helps me in estimating my mu2. And this is even more extreme, and by the same argument, when the correlation is 0.9, so a very high correlation. So y1 is highly informative for y2, and because in my maximum likelihood estimate of mu2, I'm taking the information, all information that I have from mu1, so actually I'm estimating them well here, not. And now, okay, let me break the assumption of ignorability. Okay, now I will simulate data that are missing not at random. And we see that here both maximum likelihood and complete case analysis, even when observations are the observation, sorry, the variables are independent, the estimates are not good, they are completely biased. And the same for a correlation of 0.5, and MLE does slightly better when the correlation is zero point 0.9, because we are using information of y1, right? And even if data is missing or data are missing not at random, because now they are highly correlated, the information that I'm using somehow helps me in estimating u2, but still the estimates are still biased, right? So most of my estimates are smaller than the true value. Okay, the histograms I forgot, but it to say, but it's the usual setup is for the 1000 data sets we have estimated our mu2, and this is the histogram of the 1000 estimates. And some final remarks. We have seen in this video and in the last lecture that under ignorability, maximum likelihood estimation can be validly obtained by maximizing the likelihood of the observed data. We have seen in this part a specific example where we were able to factorize the likelihood of the observed data, and so we were able to obtain analytically the estimates for the parameters. And as I have already mentioned, general missing data patterns, they sometimes do not allow an explicit factorization. And even if we are able to factorize, if the parameters are not distinct of the factorization, and they don't need to be, then I cannot use the trick of maximizing the different terms separately. And in the next video, and we will start learning the EM algorithm, and we will keep studying it next week. And I'm sorry, the EM algorithm is a very general iterative procedure, specially designed for incomplete data problems. And sorry, it's not COVID. It goes without saying that we have talked about ignorability, maximizing the observed data likelihood. If data are MAR and parameters are distinct, I can maximize my likelihood of the observed data. But at the end, and this goes to a fundamental question, my estimates will only be as good as the model that I use to my sampling distribution, right? And this is not a problem, a specific problem for incomplete data, but the model that we specify needs to agree with the data that we have, right? So even if we are able to maximize the likelihood of the observed data, is if our model is not well specified, well, it doesn't matter. Even if data is missing completely at random, we will have estimates that are biased and not valid. But just to make this point, and okay, see you in the next part to start learning about the EM algorithm. Thank you.